Okay. It's a pleasure to introduce you Héctor Cánovas. He studied here. He graduated from University of La Laguna in 2007, so probably some of you know already. From here, he just moved to Utrecht to do his PhD on high contrast imaging of protoplanetary disk. And when he finished his PhD, he moved to Valparaiso University in Chile, where he did also work on protoplanetary disks using ALMA. And now he's in Universidad Autónoma de Madrid, and he's using ALMA and SPHERE, and that's what he's going to talk about today. Okay.
Hola. Yeah. Good morning, everybody. Thanks for coming to my talk. In the next minutes, I'm going to show you direct images of protoplanetary disks that we think that show signposts of planet-disk interactions. And I say we think because so far we haven't been lucky really detecting a planet interacting with the disk. Many of the images I'm going to show you have been obtained either by my collaborators listed there or by myself. We've been using mainly ALMA and SPHERE. ALMA is probably the most ambitious telescope we have right now. It's a huge observatory. And SPHERE is a second generation instrument placed at the VLT. And SPHERE was designed to detect exoplanets embedded in disks. And so far SPHERE hasn't been also really lucky with this. In any case, I'm starting directly, going straight to the point. When I look to the statistics of planet detections, I kind of feel envy about my colleagues working with exoplanets. To date, there are more than 3,000 exoplanets directly detected, and this is a huge number. This means that planet formation is probably something kind of common, it's not rare, and also with such a huge number of detections, we can start doing some statistics, and we can start getting an idea of the planet population that we have out there. We see that the planet population is kind of very heterogeneous, and this is what I'm plotting here. Here, every point represents a detected exoplanet, and I plot them as a function of their orbital semi-major axis and a function of the mass of their stellar host. In case you wonder, this point here represents the position of the Earth, so one planet orbiting at 1 AU. Also, in case you wonder, the 7 points corresponds to the 7 exoplanets detected in our neighbor, Proxima Cem. Now, you can see that, again, all these points are spread all over the plot. And on the other side of the picture, it is the people like me working on protoplanetary disks and trying to understand the conditions for planet formation. And we have a problem in the sense that, unfortunately, there are not so many disks with good images. This is a kind of nice collage. In total, we have something like 30, perhaps 40 disks with very detailed images. So it is very difficult for us to connect what happens at the early stages to what we observe in the later stages. And this is kind of our holy grail. This is what we want to really understand. What happens at this stage that brings us to the observed population of exoplanets? This is what we are, all our communities, trying to find out. Well, this is the layout of the talk. First, I will present briefly, introduce ALMA and SPHERE and explain you why they are so important for us. Then I will talk a bit about planets and disks in general. Then I will show you some interesting images of young disks, because at the beginning I didn't pay really a lot of attention to them, but apparently they are very important for planet formation. And then I will focus on transitional disks, which are the disks that most of people like me are studying. Okay, so why ALMA and why SPHERE? The thing is that the two instruments are very complementary. Here I'm showing a sketch of a protoplanetary disk. It's something quite flat. Well, it has what we call the flare angle. It has a young pre-main sequence star at the center. And the thing is that with ALMA, we are sensitive to radiation from cold grains. Simplifying things a bit, with ALMA we are sensitive to large grains, millimeter-sized, typical, and these grains are located in the disk midplane, more or less here, and far away from the star. So they are shielded from the stellar radiation and from the radiation from the interstellar medium, and they are cold, with typical temperatures of 20, 25 Kelvin. So ALMA is very, very powerful in detecting this type of grains. Now, on the other hand, we have the disk surface, which is here, and the surface of the disk is populated by small grains. They are typically porous, and they emit mostly in the optical and near infrared. So with instruments like a SPHERE, we are very sensitive to the light of these grains here. And what happened is that when we observe one disk with both instruments, being sensitive to different types of grains, what we see is not necessarily the same. And this is a real example. This is an ALMA image of a disk around a very big star, one a bit more massive than one solar mass. And this strange shape here is what we call horseshoes. This type of shapes became really famous during last years. And what we think is happening here is that the large grains in the disk midplane are trapped in here. Here, the red means the higher density of grains. And we see that this, well, is a strange shape, at least at first sight. And then we see the star should be located here. I forgot to mention the disk. In this case, is face onto you. It's looking to you like this. And what we see here is no grains in the inner part. So there is an inner cavity. And again, these grains are distributed in, horseshoe. Well, whatever you want to call it. Now, if we observe the same disk with a SPHERE, so if we trace the surface of the disk, it looks like this, quite different. We see the negative part here means that there is no emission. We are tracing again small grains, so there is a huge cavity. In case you're wondering, the cavity size is 140 AU. You should remember that the distance to Neptune is 40 AU, if I'm not wrong, so this is a huge cavity. And here we are seeing the inner wall of a disk, so imagine this part, being directly radiated by the star. So the spatial distribution of these small grains has nothing to do with these ones. So again, combining the images from ALMA and SPHERE or complementary instruments, we can get an idea of the three-dimensional distribution of the disks. Now, apart of being especially complementary, these two instruments are also complementary in the sense of tracking the temporal evolution of the disks. This is, of course, a simplified sketch. But what we think is that the early stages of the disks are what we call the class 1 stage. We have a very strong accretor star surrounded by a massive disk, and everything is surrounded by an envelope, which is typically optically thick in the optical and near infrared. It's something very massive. And with instruments like a SPHERE, we cannot see it. We cannot pierce through the envelope. But ALMA can do that. And actually, it did it a couple of years ago. It obtained this image, which I will go back later on. This is one of the most famous images of a disk. It's HL tau. So again, with a SPHERE or other instruments in the optical, you can forget it. It's very difficult to see that. Now, as the disk evolves, the envelope dissipates either by photoevaporation or accretion, and the system enters what we call the class 2 stage. This is my favorite stage because I think it's easier to find out what happens there. It's a stage where we think that planets are forming, and in this stage is where ALMA and SPHERE are really complementary. Again, because if you remember from the previous slide, we can really trace the structure of the disk. Now, as the system evolves, the system becomes what we call a debris disk. A tenuous, faint disk is something like this. Most of the disk has gone. If planets have ever formed, they are there. And this is the realm of a SPHERE and instruments like that, like GPI at the Gemini, like Subaru as well. Because if they are planets, it's kind of more easy to image planets in there. And I will briefly talk about planets and disk in general. This is a kind of very standard slide for me, but yesterday I was talking to Arturo and I realized that perhaps not everybody is aware about that. Right now we have direct images of exoplanets. All these points here are exoplanets. We don't have that many of those. I think actually a few more than this, or perhaps only these three. And these are, of course, very, very well-known systems. Here is a multiplanetary one. This is the famous Beta Peak. The planet is in here. And this is Fomalhaut. Some people call it the Eye of Sauron, so by obvious reasons. Now, the thing is, all these disks, all these objects, are debris disks. They are surrounded. There is a very tenuous and faint disk of dust. There is almost no gas. And then it's kind of easy to directly, relatively easy, to image a planet in these objects. Because you don't have all the emission from the disk bothering you. right? And also, of course, detecting planets in every disk is give us confidence that planets really are born in protoplanetary disk. Now, if we want to understand how planets are born, as I do, we want to go to the earliest stage, protoplanetary disk stage, when we have gas-rich and dust-rich objects. And the situation is way more complicated, because we have all the light from the star plus all the light from the surrounding disk. And it's extremely complicated to separate all these components and isolate the light from a single planet. And so far the situation is not really good, in my opinion. I hope it improves. Those are the best candidates, if I'm not missing, in the planetary regime. There are some candidates in the Browndorf regime, but I'm talking about planetary mass objects. This is famous one, is observing L-band, HT 10546. And the candidate is this thing, it's not even a point source. What we think we are looking at is perhaps circumplanetary disk is hot by the effect of the planet. And there are several other observations confirming this candidate. And now, a couple of years ago, it appeared this one, LKK15, 3-point sources on a famous disk. This is the disk around it as imaged by the VLA. You can see an ellipsoid here, bright light. And the thing is that, well, one of the planets here is known to be accreting. It's been detected in H-alpha, which traces accretion to the planets. But the other 2-point sources were detected using a complex technique. They use interferometry in the optical. So those are reconstructed images. The coverage of the UV plane is not so complete. So perhaps, that's my opinion, I think we are looking at something more like an artifact or perhaps a scattered light by the disk. So far I haven't seen direct images of these planets being confirmed right now, and this paper came like 2 years ago. The community I think is waiting for something like this to come. And then we have different types of objects, the planetary mass companions and also free-floating planets. Planetary mass companions are rare, are funny, are objects that have a mass in the planetary regime that is below 12 Jupiter masses, but they are like this guy here. They are very far away from the central stars, something like 300 AU, and it's very difficult for current theories of planet formation to explain how they are there. And some of them are accreting like this object. So if they are accreting, it means that they are surrounded by a circumplanetary disk. And so far there are not many images of circumplanetary disks. We were lucky and we published one of them 2 years ago. Claudio Cáceres was my office mate. And what we see here, this is an ALMA image. Here in the cross is the position of the binary. And we don't see any emission associated to the binary, but we see gas and dust associated to the companion. So probably this is one of the strongest detection of a circumplanetary disk. In case you wonder, probably we didn't detect the disk around the binary because disks around binaries are thought to disappear faster because of the effect of photoevaporation and tidal effects, etc. And now I'm going to speak a bit about planet formation, why disks at earlier stages on what we call the class 1 stage are important for us. Well, there is as I said before, the very famous image of HL Tau from ALMA. And just for fun, I'm going to ask Tobias, who I know. Here we have one real image and 3 models. Can you tell us which one is the model and which one are the observations? Only one is the observations. Can you pick up the real observations? Which one? Wow, yeah. For a solar physicist, no. Wow. Okay, so this image was published 2 years ago, if I'm not wrong, and it was the best image obtained so far about the protoplanetary disk. They obtained it with ALMA in the most extended configuration by that time, so it's the one with highest resolution. First of all, we were all surprised to see a disk with bright and dark rings on it, and at that stage, at the class 1 stage. Remember that this object is actually surrounded by a huge envelope. And since this image, I would say everybody freak out a bit about this object. Since this image, there are like 10 or 15 papers dealing with simulations trying to explain what is the origin of these rings. One explanation is planets, but then it's difficult to say how is possible that planets are formed in such an early stage. That came as a surprise. But again, so far, no planets have been detected. There are different options to explain the rings, like sintering, which is a way for grain growth, and other ones. But for me, a part of this image, then this year came another very famous image of disk. This time I'm not asking you to deal with models, Tobias, relax. This is TW Haya. It's a much more evolved disk. This guy here is 8 million years. This one is less than 1 million year. It's both, I think they are the most studied disks in our field. And you can see that with ALMA we see the same features. So I always wonder how it is possible. It means that this survives up to here? I don't think so. What is causing these things? So far, again, no planets detected in TW Haya. So we don't really know what's going on. And this is the SPHERE image, which was published a few months ago, or maybe 1 year ago. They are again complementary. Remember, with SPHERE we are tracing the upper part of the disk. With ALMA we are tracing the mid-plane. This is a zooming in the center, so it seems that there is a small cavity, as we expected from photometry, and it seems that they are perhaps streamers. There is material flying onto the star. But this is what I wanted to say about the last one. No, I forgot to mention. A part of searching for signposts of planet formations, last year we found that there are some things that are, there are some phenomena happening in early stages that are probably very important for planet formation. This is an F-February star, V883, and F-February stars are nearly class 2 objects, but they are still very young. And their main characteristic is that from time to time, there's all of a sudden outburst. What we think is that all of a sudden they accrete a lot of material, and then the star shines a lot. It releases a lot of energy, it brightens a lot, and then the temperature of the whole disk is increased. We observed this object right after an outburst with ALMA. And this is what we saw when I look at the screen with Lucas Ciesa first time. I was like, okay, this seems like, if you can see, it seems that there is a kind of gap here, but yeah, not really sure what we were looking at. Then we began with the analysis, and it became clear there are two different regions in this object. There is a bright inner region and a kind of faint halo. This is what we are tracing here. And now I'm not going to enter in all the details of the model, but the thing is that with ALMA, you can get constraints on the properties of the dust particles. So we combined these images, we analyzed them, and we came to the conclusion that these two regions here represents two well-differentiated regions in the disk. There is the region outside, where the dust particles are covered by a thin layer of water in the form of ice. However, in the inner region, we have dust particles without any ice, and this is crucial. This is very fundamental for theories of planet formation. We think we are looking to something like this. Why this is crucial? Well, first of all, let me tell you the definition. The imaginary line that separates these two regions is what we call the water snow line. It's something that many people is studying in detail. And this is important because when the grains are covered by a layer of water ice, when they collide with each other, they stick with each other, and then it's easier for them to grow. However, if the dust grains do not have that kind of glue, when they collide with each other, probably they become destroyed, smaller particles. Now, the surprise is that when we did our analysis, we compared with models published just 1 year before by Vansati and colleagues. This is their model. This is one parameter describing the grain properties. According to our observations, the water snow line in this object is located at 40 astronomical units. And this is really unexpected, because the water snow line, the location depends on the disk temperature, and the temperature depends on the stellar temperature. So you can work out at which distance do you expect the water snow line to be. And we were expecting the water snow line to be at 5 AU, but again we found it at 40. So the best explanation we can is that, okay, we observed this object right after an F-February outburst, the temperature of the whole thing increased, and that push away the water snow line location. Now, this is very important because we think that many objects, like our sun, go through F-February phenomena, outbursts, several times when they are young. And that means that the water snow line is probably dynamical. So the region where the rocky planets form changes, then the disk, the star and the disk cools down again, the water snow line move again to 5 AU, so that region gets small again, and then when the system suffers another outburst, changes. So that, of course, should have a very strong impact for planet formation theories. And now I'm moving to transitional disks. Those are the objects I mainly work with. Transitional disks are known since quite a long time ago, but it's only since a few years ago that we are studying them in detail. To define what is a transitional disk, we have to look to its spectral energy distribution, to the SED, and this is what I'm showing here. Here we have the photosphere emission, and this is photometry from different satellites, from different observatories. Obviously here is the hot region, and as we move here, we are tracing colder emission. And what I'm plotting here, this is the median in gray, in this region here. This is the median emission of class 2 disks in the Taurus star-forming region. And if you look to the photometry of this object, you see that there is a deficit of emission here. The photometry is here, and compared to the median emission of many other objects, is below what we were expecting. This is not new. This is the definition of a transitional disk. Are objects that have less emission in the near infrared. And the explanation for that is that we have full disks where they have material all the way close to the star, and the material close to the star is hot, and therefore it emits here in this region. But then we have disks with inner cavities or gaps. There is a lack of dust near the star, and then there is less emission. So those will be transitional disks. Now, this terminology was coined almost 30 years ago by Strom et al., 89. This is a really nice paper. It's one of my favorite. They were observing with IRAS, and they did observe a sample of stars. And yeah, they realized that some of the stars, I just mentioned, they have a deficit. And they, already by that time, they mentioned that that was probably linked to disk clearing mechanisms. And they already hypothesized that perhaps these objects are in transition to the debris disk regime, perhaps by the effect of planets. And now we have images, and this is a real zoo. As I mentioned, transitional disks became more famous in the last years because our imaging capabilities have improved a lot. And what we see, to me, is astonishing. These images are really amazing. When I did my PhD, I couldn't ever imagine we would be obtaining images like this. They were really blurred, really like, okay, you have to work out the image of the structures that you see here. Some objects have spiral arms, very much like galaxies. Other objects, this is a ring, a huge ring, nearly perfect. This is a face on disk with a huge cavity. Other objects have, as TW Haya, they have multiple gaps inside. Other objects have cavities, then a bright emission, then a gap, then whatever is beyond. The horseshoes that I mentioned, this is an extreme case of a horseshoe. So in short, it's a very heterogeneous population. It's difficult to me to say, okay, those are all the same family and they will evolve in the same way. Each one appears to do different things. And perhaps this is reflected on the planet population that we observe, but this is pure speculation, of course. So there are some mechanisms proposed to explain what we observe, mainly the cavities, because the detailed features, let me go back just one moment. The detailed features like spirals and so on, they've been appearing only in the last years with strongest imaginary capabilities. But for sure, what is the cavity itself, this with cavities, these were the first one to be detected. So at the beginning, all people in our field was trying to explain the origin of the cavities. So I begin with this plot, with this table. There are different mechanisms that can explain the observed cavities in the transitional disk. First, we have photoevaporation. We know photoevaporation is happening all the time. Depends on the amount of X-ray, UV emission. This is not well calibrated yet, but we know that because of the energetic radiation from the star, the grains at a certain point the grains and the gas will evaporate. So, depending on the cavity size, and up to few tenths of AU, photoevaporation can work. But photoevaporation cannot explain gaps. A gap is a discontinuity. With photoevaporation, you cannot explain that you have dust really near the star, and then you have a gap, and then you have the rest of the disk. You can explain a continuous cavity, but not a gap. Neither spirals, neither horseshoes. Then we have grain growth that we know is happening all the time. So if the grains grow in size, we will see a quick decrement in opacity. So we could observe an inner hole. But again, grain growth, the same. Cannot explain it, all what we observe. Binarity can explain many things, but not gaps. And then it's planets that, in principle, they can explain everything. With this, I'm also very careful. I mean, we know that there are planets because of all the detections, but I'm afraid that many people, including myself, sometimes are trying to explain everything with planets. I remember when I was at the university, Fernando Perez was teaching us fluids, and he said, in astronomy, when you don't understand something, you can always quote the magnetic field. And I think we are doing something similar with planets, if you allow me to do that joke. And now we have dead zones, which are actually magnetic fields. In the disk mid-plane, and dead zones is something kind of difficult to explain. Are regions in the disk that are shielded from the radiation from the star, from the outside, and the magnetic field changes in that region. And this is a kind of simple table, but then we go to the complex table. So with growing imaging capabilities, we are observing things that, to me, have no explanation without planets or without, otherwise I don't know what to call. We see systems with multiple rings, like this one. This image came, this is an SPHERE image from last year. Then we see systems with what it seems broken rings and gaps and all kind of complex structures. Then in the gas, well, in this talk I'm talking mainly about the dust because this is the region where I work. But in gas, we've been observing also really amazing structures. In the gas here, you see this kind of S shape. This is the signature of a non-Keplerian flow. In principle, if you have a companion orbiting near the star, the companion can bother the Keplerian flow, and you can see signatures like this. Then there are disks where we see gas flows. This is only one single image with ALMA, but you have to believe me. There is a disk around here like this, face onto you. And with ALMA, we can trace dense gas as it moves at different velocities. So in this case, it's a disk with a huge cavity similar to this. And in one snapshot, we saw dense gas connecting. Like if we would be this disk, we are looking at dense gas connecting the outer part of the disk with the inner part. And this was also expected from models. And then we have disks that show evidences of shadows. And this is this one here. There is the dip here. It could be a discontinuity, but we have compared this with other observations, and there are many other disks that show evidences of shadows. That means that there is something in the inner part of the disk that you cannot see. There is something optically thick. It has to be a large structure that is able to cast a shadow over the disk. Something very complicated, but we know it's happening. I'm really not making up this thing. So in short, a lot of complex features. Now I'm going to speak in detail about two transitional disks that have taken most of my time during the last years. First, we have Schwarz 91. Sometimes I love it, sometimes I hate it because it gives me some problems. It's located in the Lupus star-forming region. All the disks I'm mentioning are in our neighborhood. They are not further out than 250 parsecs from us. And it's simply because disks that are beyond that distance are difficult to image. So all the people like me are studying disks in nearby star-forming regions. This one is an M-type star. I'm mostly focused on T Tauris stars, M-types, K-type stars, and just briefly telling you a bit about these properties. 200 parsecs in the Lupus star-forming region, 4 million years old. The mass 0.6. This is of course model dependent, but it seems that this below the solar mass, and it is accreting. It means that the star is eating part of the disk that surrounds it. And it was first identified as a planet-forming disk candidate by Matthias Reiber and Lucas Chiesa, who were the people I was working with in Valparaiso. So I arrived to this group, and luckily for me, they already had ALMA cycle 0 images, and this is what I started working with when I moved to Chile 5 years ago. This is the ALMA image. Cycle 0 is nothing exciting. When I saw it on my screen, I was not excited at all. I didn't see anything particular about the object. But then working on it, as you will see, I became more and more interested. This is the SCD. Now you can see that, again, I would expect, if the disk wouldn't have an inner hole, I would expect emission in the infrared to be lying around this region. But we see this is the photosphere, and we see that there is no excess about photospheric levels up to 10 microns. This is a very strong indicative of a huge inner cavity. And then we see a large jump in here. I'm using this sketch to help myself. So we have information about the overall disk structure from the SED. And then we have information about the distribution of the large grains in the disk mid-plane from this ALMA image that at first sight, it looks a bit crappy, right? Now, again, with a Spitzer near-infrared photometry, we get information about this region, the region close to the star. This tells us whether there is dust or not. With Herschel and this jump here, we get information about the wall that is directly illuminated from the star. And then with ALMA, we get information about the overall structure of the disk midplane. So what did we do? We ran a lot of models, more than 2,000 models. We use a genetic algorithm to create a parametric model. This is not a physical model in the sense that we didn't run hydrodynamical simulations, but we create a parametric model within that was physically meaningful, and we try to simultaneously reproduce all what we had. We try to simultaneously fit the SED, and this is what I'm trying to explain here, and also we try to simultaneously match the ALMA cavity. Well, because it was a cavity, as I will show now. And we ran that, we use radiative transfer models. Again, we use a genetic algorithm, 2,000 models, and we end up with a model that successfully reproduces everything. And it was like, this is the model that we end up. And it's important to keep in mind this image. This is the observation, and this is this model. We concluded that there was the disk, Schwarzschild-1, had a huge cavity, something like 100 AU in size. And this is really, really huge. Again, remember that the distance to Neptune is like, the average distance to Neptune is 40 AU. In our first model, what we published in 2015, it looks like a ring, but it's not a ring. The disk actually drops smoothly, following an exponential profile. Drops smoothly as you move far away. Now, when you convolve our model, or actually when you plug it through the ALMA simulator, reproducing our observations, it looks like this. Very similar to what we observed. And just to further convince you that it was a good model, we subtracted and we saw nothing but noise. So we were kind of really happy with this thing. And when we include the information again about the SED and also information about the gas that I don't have time to mention here, we concluded that the structure of the disk was something like that. It had a huge cavity, we quote 97 AU. Then there was a region near the cavity populated by small grains, and then there was a huge depleted inner region, and then the disk beyond that. And all of this is really consistent with models of planet formation, because the modelers are telling us that if you have Jupiter-like planets orbiting at this region, they will create what we call the dust filtration mechanism. It's something difficult to explain, but because of hydrodynamical reasons, the planet creates something like a pressure wave that keeps the large grains further out from the planet as the planet is orbiting inside of the cavity. But the small grains are allowed to go a bit more inside. So with modeling in mind, we decided, okay, it's time to go for new observations, with more detailed observations with ALMA in cycle 2. And then this time, this was exciting. This time I really got excited because this is a real image that was actually confirming our observations. What we observe is a narrow ring of dust, and here the contours are the gas. This is the gas. We see a disk in Keplerian movement, and the dust particles, the millimeter-sized particles, are confined in a very narrow ring. It's peaking at 110 AU. We think we don't resolve the disk in the ring in our images, but we can estimate how thick it is. It's something like 30, 40 AU at most, if I'm not wrong. And this was really, really consistent with the predictions by modelers like Paola Pinilla and others that were trying to reproduce the effects, again, of a giant Jupiter planet orbiting inside of the cavity. Now, what we think is happening is that here we have the gaseous disk, much larger than the structure that we observe, and the small grains are coupled to the gas. So as the small grains feel the gravity from the star, they move inside. Of course, I'm simplifying a lot, right? They move inside, and if there is a giant planet in here, the pressure created by that planet makes them to pile up in a narrow ring region. And this is again hypothesizing a lot, but perhaps here this is a very good region to form more rocky planets, because we have a narrow spatial region full of dust grains. Now, with this in mind, I got the DDT time to observe for planets with NACO, L-band, last year, but I also got 15 nights of bad weather, so the telescopes didn't open, so very bad for the DDT, but it was just re-observed a few weeks ago, and I haven't had the time to look at the data. So perhaps in a few months I can tell you that there is a planet that will be extremely happy. Let's see. Yeah, but to finish, now another very interesting object, G1604. This time I didn't observe it with ALMA, but I observed it with a SPHERE. This guy is located in Upper Sco. It's at 145 parsecs from us. It's a famous star-forming region. Again, some details about it. It's a low-mass star. It's a T Tauri. It's a K2. The age is quite uncertain, between 5 or 12 million years. Depends on the models. I believe it's older than 5 million years, actually. And it has very, very tiny accretion, and this is really interesting, as I will show now why. The thing is, the system has been studied in great detail. When you look at the SED of the object, it has the typical spectral energy distribution of a transitional disk. People knew that it had a huge cavity, and this is the ALMA image. The disk is looking face on to you, so it's very nice for direct imaging. And the cavity in the large grains, in the millimeter-sized grains, is nearly 80 AU. Huge. It's not as large as the previous one, but it's really huge. And now, a Japanese team with a Subaru, they observed the disk in polarized light. And this is what they saw. A ring with a discontinuity, and remember, right now it's located here. This is important. A very bright ring. And here, the dashed white line is the same size. It's just to show you that the cavities are different in the millimeter regime than in the near infrared regime. This again suggests what we call dust filtration. Very strongly suggests that if we have a giant planet here, the large grains will be kept further out from the planet, but the small grains can enter, can go a bit closer in. And I'm not showing gas observations because those are complicated, but with ALMA we know that there is a 30 AU cavity on the gas as well. So there is an inner cavity somewhere in here in the gas. And not only that, it's really gas depleted. And all of this is like a huge flag telling you there is a giant planet here. Okay? So with this in mind, we went to the VLT, and we were lucky this one of the few objects that was not banned from the GTO of the SPHERE, because the GTO of the SPHERE had like all possible disks with planet candidates, but this one wasn't. And yeah, this is myself when we were at the telescope, and it was amazing. We saw the disk on live, on the screens. This is not even reckoned. These are the screens that tell us if the observations are working well. At first sight, we thought that it was an AO artifact, but then, yeah, a few minutes later, a few seconds, we were convinced that no, this is the disk. This is Julien Girard and other colleagues. And those are our images. Just to let you know, our observations were devoted to detect planets, so we use a kind of different approach. But the data was so good that we were able to directly see the disk, and this is what you see here, the disk in scattered light. Here the colors are blue is very low emission, and the emission peaks at the red. This is the disk directly observed at different wavelengths. Our best data set is K or H, and then because of the instrument itself, when we go to shorter wavelengths, and because of the coronagraph that we use, we have a lot of contamination. And that's what you can see here, a lot of contamination from the inner mask. But in all data sets, you can see clearly a ring, a narrow ring, which is a wall directly illuminated. And now keep an eye on this. Again, the discontinuity. And this is the same disk. This was observed in 2012. The dip is here. And this is in polarized light, low signal to noise, but they also see a dip in here. We don't know what's going on, but we know that the dip, this is for sure is not an artifact of the data reduction, it's rotating. It's not rotating following any Keplerian rotation. I know there is a paper coming by with more observations, temporal observations, and they see that it is rotating. There is something close to the star that must be optically thick. Perhaps in my paper I hypothesized it could be a circumplanetary disk, but from what I've heard, again, this is not rotating following any Keplerian motion, so we don't know what it is. Perhaps it's something completely random, but again, it's real. Now, again, my observations were devoted to detect planets. I wasn't expecting this. These images came like a present. When we apply our algorithms to detect planets, we detect nothing. This was sad news. During the first reduction, we thought we had a planet, but at the end it was a bright speckle, so nothing to do. This is the post-Prost image. Here I'm just showing the structure of the disk with the contours, and this is a black gap at the position of the shadow. And these are the contrast curve that we obtained. This is the raw PSF. These are previous observations. And in short, beyond 0.2 arcseconds, we reach a contrast of around 12 magnitudes by integrating in the YH regime or a K. Depends, those are technicalities. The thing is that when you don't detect the planet, you can use some models to translate your non-detection limits, assuming certain age and certain set of parameters. You can translate that into planet mass limits. And this is what we did. There are two leading scenarios for the formation of planets. One implies a hot starting scenario. And if, in short, it means that, well, at the beginning the planet is hot, as the name says, and that translates in a higher brightness. So hot starting scenario is kind of more positive for us. The predicted fluxes are in principle nearly reachable with current instruments. And then we have the warm or nearly cold star scenario, which is more pessimistic. We apply both, and here is what we obtain. The region here represents the uncertainty on the age, because in this paper we, as I mentioned, the age of the star lies between 5 and 12 million years. So we said, okay, what if the planet have between 5 and 12? What we would see. And what we concluded is that with our observations in the most positive scenario, we should have detected nearly 3 Jupiter masses in nearly all inside the cavity. Here is 20 AU, is more or less from here to here, the region where we expected the planet. And we detect nothing. In the worst case scenario, okay, we are a bit worse. We are sensitive only to 7 Jupiter masses, but again, we don't detect anything. So I don't know what's going on with the system. What I wrote is perhaps there are multiple Neptune-sized planets in the cavity. That's one option. Perhaps the models are too optimistic and actually planets are much fainter than what we expect. And that means that with instruments like SPHERE and others, we have very little chances to detect planets surrounded by protoplanetary disks. Or perhaps the planets move really quickly to the inner regions of the star. And then it's not a problem of sensitivity, but of spatial resolution or coronography. But so far, if you look at the statistics of planet detections in disk with a SPHERE and other high contrast instruments, we are not being lucky. We were expecting to have detected many more planets embedded in disks. And yeah, about to finish, I think one avenue to connect planets and protoplanetary disks is combine ALMA with Gaia. And this is because there are not so many disks that we can study in detail, because again, we are limited to stars that are close to us at 250, 300 parsecs. If we are, well, 300 parsecs is already a lot. So there are not that many disks that we can study in detail. So we have to try to get the general picture. So with ALMA, we can wait, as we are sensitive to the emission from the small grains, we can estimate the total mass of a disk. And of course, we expect that more massive disks can easily form more planets or larger planets. But right now, we don't know the distances to each individual star, and that translates also in a lot of uncertainties on the ages and so on. And I think that is going to change with Gaia. In future data releases, we expect to get a lot of distances from stars in the star-forming regions and connecting everything. Perhaps we can start breaking a lot of degeneracies and start obtaining more accurate measurements of the total mass of a disk. Let's see, this is just to come. Well, I finished with the slide that I started. The situation again is like this. People like me are really interested in connecting this with this. I hope in the next years it will change. And well, thanks for listening to me. Okay.
Thank you, Héctor, for the nice talk. Do you have any questions?
How long this may last?
The disks. We think no more than 10 million years. We know that it depends, but roughly 10 million years. Within 10 million years, most of the gas and the dust dissipates, and the disk enters what we call the debris disk regime. So that's also a time scale for planet formation. In principle, it cannot take more than 10 million years.
Okay, so thank you for your talk. I have seen very interesting things in your talk. One particular that I think is solution of what you have shown is that the snow line is dynamical and moves.
Yeah.
And okay, looking to all the details about that, the other conclusion maybe of your talk is that the planet formation is very fast. Could be even in scales of 1 or 2 million years.
Yeah.
So what I wonder is that joining all together, I don't know if one of the conclusions could be that it's very difficult to form a planet like Jupiter by core accretion, because we have to form very fast, and even it's very difficult to form at the distance where Jupiter is formed because the snow line is dynamical. So what do you think about this question? So do you think that maybe very giant planets are formed in a different way, or?
Well, if they don't fall through the core accretion, which is the mechanism that I see that people like most or cite more, then we have gravitational instability. But for that, we need massive disks. And when we observe, when Lucas was the PI, the goal of observing the FUORI object with ALMA at the highest resolution, it was to detect signatures of gravitational instability, because we knew it was a very massive disk, and we wanted the resolution to see clamps. Because one of the ideas is that if you have gravitational instability, you can observe with ALMA localized clamps. Then we saw the image, which was something completely different. But I know there are efforts to detect disks under gravitational instability, and so far, no clamps. I've seen many people also doing simulations, but again, observational, it seems, at least it seems more difficult to detect disks under gravitational instability. And this is what you need to form Jupiters far away and then move. So for now, I don't dare to to tell you more.
So maybe now the major conclusion is that we don't have a good model for Jupiter. Or
What?
Maybe now the conclusion is that we don't have any good model to explain Jupiter.
Yeah. Yeah.
Other questions? Okay, I think we can conclude here, and I remember you that at 11:30 we have the scientific coffee in the library. Thanks again.
Thanks.